The world of physics has long been defined by the towering achievements of Albert Einstein. His theory of relativity redefined our understanding of space, time, and gravity, giving humanity tools to explore the cosmos. For over a century, his work stood as a cornerstone of modern science, shaping everything from GPS technology to black hole research. However, recent advancements in quantum computing are shaking the foundations of physics, challenging Einstein's most cherished principles. These devices don't just outperform classical computers, they operate on rules so strange they force us to rethink reality itself. To grasp the significance of quantum computing, we must first understand classical computers. Traditional systems use bits, representing either a 0 or 1. This binary language powers everything from smartphones to supercomputers. Every calculation, app, or video stream relies on this simple on-off logic. Quantum computers, however, use qubits, quantum bits, which exploit superposition. Unlike a classical bit, a qubit can exist in multiple states at once, like a coin spinning mid-air, neither heads nor tails but both simultaneously. This quantum advantage allows these machines to process vast amounts of data in parallel. Problems that would take classical computers millions of years, like simulating complex molecules, could be solved in hours. But superposition is just the start. Entanglement, another quantum phenomenon, links qubits so that changing one instantly affects its partner, even across vast distances. Einstein called this spooky action at a distance, and rejected it, believing the universe was orderly and deterministic. His famous quote, "God does not play dice," reflects his discomfort with quantum mechanics' probabilistic nature. At the quantum level, outcomes aren't fixed but based on probabilities, defying Einstein's vision of a predictable cosmos. For decades, these ideas remained theoretical, debated but untested. Today, quantum computers turn theory into practice, solving real-world problems and exposing gaps in classical physics. One groundbreaking application is simulating quantum systems. Classical computers struggle with such tasks because the math grows exponentially complex. Quantum computers, however, thrive in this environment. In 2023, simulations revealed discrepancies in how quantum particles interact with space-time at tiny scales. Einstein's equations work flawlessly for planets and galaxies but falter in the quantum realm. Here, space-time, described by Einstein as a smooth fabric, appears pixelated, like a digital image. This idea, called quantized space-time, isn't new. Theories like loop quantum gravity proposed it decades ago, but proof was elusive. Quantum computers now offer tools to test these ideas, suggesting space-time might emerge from quantum interactions. If true, this would rewrite our understanding of the universe's structure. Another challenge to Einstein's legacy involves causality. Classical physics assumes a clear chain of cause and effect. Quantum mechanics, however, introduces indefinite causal order, where events lack a fixed sequence. Imagine two events, A and B, occurring in a superposition. Neither clearly happens first. This blurs the line between past and future, questioning whether time is fundamental or an emergent property. The implications are profound. If causality isn't absolute, our understanding of free will, destiny, and history could transform. Quantum computers are probing these questions, revealing a universe far stranger than Einstein imagined. Even consciousness is under scrutiny. Some theories suggest it arises from quantum processes in the brain, like entangled neurons. While speculative, quantum simulations could test these ideas, merging neuroscience with quantum physics. Beyond theory, quantum computing poses practical risks and rewards. Current encryption methods, like RSA, rely on the difficulty of factoring large numbers, a task trivial for quantum machines. A quantum-powered cyber attack could cripple banks, governments, and infrastructure. Conversely, quantum encryption uses entanglement to create unhackable networks, where eavesdropping alerts users instantly. The global race for quantum supremacy mirrors the 20th century space race. Nations and corporations invest billions, knowing control of this technology guarantees economic and military dominance. This quantum Cold War could redefine geopolitics, with winners shaping the future of AI, medicine, and energy. For instance, quantum computers might design room temperature superconductors or drugs tailored to individual DNA. Ethically, quantum advancements force us to confront existential questions. If reality is probabilistic, what does that mean for human agency? If space-time is an illusion, how do we define existence? These debates blur science and philosophy, challenging our place in the cosmos. Einstein's theories remain vital for macroscopic physics, but quantum computing reveals their limits. The quest for quantum gravity, a theory uniting relativity and quantum mechanics, is accelerating. Simulations of black holes and wormholes hint at space-time's quantum origins. The holographic principle, suggesting our 3D universe is a projection from a 2D surface, gains traction through quantum experiments. Each discovery chips away at classical notions, painting a universe built on entanglement and uncertainty. Even time itself is under revision. Quantum experiments show particles moving backward in time, challenging the arrow of time concept. If time is emergent, not fundamental, it reshapes cosmology, suggesting the Big Bang might be one phase in a cyclical multiverse. Such ideas were once science fiction but now enter mainstream research, thanks to quantum tools. In biology, quantum effects explain mysteries like photosynthesis, where plants efficiently transfer energy using quantum coherence. Human cognition might rely on similar processes, with entangled particles enhancing brain function. While controversial, these theories push science into uncharted territory, where mind and matter intertwine at the quantum level. As quantum computers evolve, they'll tackle climate change, optimizing energy grids or capturing carbon with unprecedented precision. They'll revolutionize AI, enabling machines that learn and adapt like humans. Yet, with great power comes risk. Quantum technologies could deepen inequality, giving elites access to tools that reshape life itself. Einstein's genius laid the groundwork for this revolution, but his deterministic worldview is giving way to a universe of infinite possibilities. This isn't about disproving him but expanding his legacy. Quantum computing isn't just a tool, it's a lens, revealing hidden layers of reality. As we peer through it, we confront mysteries Einstein could never fathom, from quantum consciousness to the fabric of space-time. The journey has just begun. Every breakthrough opens new questions, proving the universe is wilder than we dreamed. Subscribe to our channel and thanks for watching.